Welcome back. Hi everyone, welcome to PW English Medium channel and welcome to UMEED NEET English series. Friends, as you know, in this course, we are completing each chapter for NEET 2025, and in these classes, we'll cover all the important topics along with formulas and some important questions. Alright, so without any delay, let's start. Today we are going to talk about moving charges and magnetism, the chapters which are before this chapter you're going to find out the videos on the same channel, right? So today we are going to mainly talk about magnetic field. We'll start our class with magnetic field, then we'll discuss Biot-Savart's law. I'll also derive Biot-Savart's law for you and magnetic field due to a current carrying loop. Then we are going to talk about Ampere's loop, moving charges, Lorentz force, torque on a current carrying loop, and galvanometer. Please note that I have already completed the conversion of galvanometer into ammeter and voltmeter under current electricity, right? So today we are going to only talk about how really a galvanometer works. Okay, shall we start with the concept of magnetic field? How are we going to define magnetic field, right? Or we have also if you are going to look into the NCERT, in the name of this chapter is basically moving charges and magnetic field. Moving charges and magnetic field. So magnetic field can be also written as something like this. So we are going to discuss the moving charges part after we are going to discuss it in the second part of this chapter. First we are discussing about the magnetic field, but still let me give you an overview of the entire chapter. Dosto, whatever we have learned so far, that whenever you have got a charge kept at rest, we talk about electric fields, we talk about the concepts of electrostatics when charges are at rest. When charges start to move, we say that now we are going to talk about something that is called as current. Now the thing is, you all know, you have learned this thing in grade 10th, that long ago, scientists used to think that magnetism and electricity are two different concepts, right? But after the experiment of 𝐄𝐍𝐆𝐋𝐈𝐒𝐇, we know now that magnetism and electricity are not two different concepts, but basically they are same thing, which can be read as electromagnetism, right? So how are we going to basically talk about these things? Let's suppose I've got a current carrying wire over here, because now we all know what a current carrying wire basically means. Let's suppose we have got a current carrying wire over here, and I've got two charges. One is charge Q1 and another is charge Q2, and the difference is that charge Q1 is at rest and charge Q2 is actually moving with this velocity, right? And I've also told you that it is moving with certain velocity v. Now this is something that I am talking about, the observation, right? What are we going to observe? We are going to observe that there will be no change in charge Q1. Charge Q1 was initially at rest, and after some time also it will remain at rest. That means there is going to be no effect on a charge particle which is at rest, which is just beside or which is in the vicinity of a current carrying conductor. But there is something special going to happen with charge Q2. What's going to happen? See, we would have expected that charge Q2 should move along this straight path, right? Hopefully I have drawn a perfectly straight line, right? Along a perfectly straight path. But the fact is that we observe that this particle changes its path and it starts to move something like this. So this basically means that now we are talking about, if we have got a moving charge, that's what the moving, we are going to discuss this thing in moving charge part. We are saying that if we have got a moving charge kept near a current carrying conductor, a force is getting applied on it. A force is getting applied on this moving charge particle. We call that force as magnetic force. Sorry, just a second. We call that force as magnetic force. That means on this charge particle, a force is being acted. A force is acted on this charge, right? and in the region where this force can be experienced by a moving charge, please hear me out carefully, the region where a force can be experienced by this moving charge will be defined as the magnetic field, right? So when we are going to talk about magnetic field, we are going to talk about two things. We are going to talk about the magnitude of magnetic field, and we are going to talk about the direction of magnetic field. And then when we'll discuss all of these things, then we are going to talk about the force acting on this moving charge particle kept in magnetic field. So that is going to be the overview of this entire chapter. Hopefully you are comfortable with this, right? So first of all, let's talk about how we are going to actually find out magnetic field using Biot-Savart's law. Now Biot-Savart's law will also tell us the magnitude of magnetic field as well as the direction of the magnetic field, right? And we are going to also coin a special rule for this direction of magnetic field that you already know. First of all, Biot-Savart's law says, according to this law, the magnitude of the magnetic field dB is proportional to the current I, the element length dl, and inversely proportional to the square of the distance r. Its direction is perpendicular to the plane containing dl and r. What is it all about? Obviously, I will not expect you to remember this law. I'll expect that you must understand Biot-Savart's law. It is very important and you will be automatically be able to define it, isn't it? So let's suppose I have got a current carrying wire of a random shape, doston. Of a random shape, I have got a current carrying wire in which current I is flowing. And I want to know magnetic field at point P, something like this. Acha, I have got a random current carrying wire. So let me do one thing. Let me take an element over here. Now everyone knows here what element is. Okay? Let's take a small, infinitely small length. I'll call it as DL. I'll call this thing as DL. Acha, by the way, you are going to say, sir, what is this DL? We are going to define it as something that is known as current element. Something that is known as current element. Acha, please note one thing that you are going to use again and again this term, right? So current element is actually nothing. It is just I times DL. It is a vector quantity. What is going to be the direction of this vector quantity, sir? Direction of this vector quantity is very simple. It's going to be just along the direction of current at that given point. So let's suppose if you have got a wire something like this and you want to know, sir, what is the direction of current element at this point. So current is flowing flowing along this wire something like this. So at this point draw a tangent. So this is going to be the direction of current element and the magnitude will be written as current times dl. So that is what current element is. Very easy. It is a vector quantity. Its magnitude is just current times the length of that element. So right now let's move on. Now they are saying that if you are talking about an infinitely small current element, the magnetic field that will be produced because of this infinitely small element will also be very small. So let's call it as dB. So dB is basically infinitely small magnetic field, or it can be also called as magnetic field intensity or magnetic induction. So we have got three terms, right? Now the thing is, let's suppose I am drawing another vector quantity over here, which is the position vector. And this position vector is nothing but this is position vector r. Can you please again repeat what this position vector is? This position vector is the direction of this point P from this DL. Acha, this is going to make some angle with this current element. So let's say this angle is theta. Hopefully everything is clear till this point, right? I'll also explain what this theta is. Theta is the angle between current element and position vector r. And what does Biot-Savart's law says? Biot-Savart's law says that this dB is going to be proportional to I dl cross r upon r cube. So obviously you are going to say, sir, wait a second. isn't this should be r square? So this is the vector form of Biot-Savart's law. You must be able to also understand how we are going to write it in vector form, na? Because let's suppose we want to know the direction of that magnetic field. So how are you going to do it, dosto? You are going to do I dl cross r. Now please understand, this is one quantity which I am naming it as current element. So I am going to use my normal right hand rule for vector product. Now please understand, I always again and again in every chapter, almost in every chapter, I say to you that please don't forget to use your vector product. It is going to be used very extensively. How we use it? We use our right hand, we align our fingers along the direction of a vector, that is IDL. So IDL cross, we curl our fingers in the direction of another vector. So thumb is pointing inwards. Is it clear? See, I dl cross r. So thumb is pointing inwards. That means magnetic field at P point is going to be inwards. Also, many of you already know, sir, we have got something known as right hand thumb rule. So we are going to put our thumb in the direction of current. I am going to open my fingers in the direction of point P. If my fairer end is pointing into the plane, I am going to write a cross over there. Hopefully everything is clear till this point, right? Now let's move on and let's write the normal scalar form for this. So we are going to write, scalar form will be written as, first of all, proportionality constants comes out to be mu naught upon 4 pi. This will be I dl sine theta. One of the r can be cancelled out by this and this will become r square. So this is the scalar form. This is the scalar form. So nothing to worry about. This is going to be the scalar form. Next is what is this mu naught upon 4 pi stands for. So this mu naught upon 4 pi is nothing but it is a constant. It is a proportionality constant whose value is 10 to the power minus 7, 10 to the power minus 7 Tesla per meter, right? Tesla per meter per ampere. So we'll write it something like this. Or you can also write it in Weber. So this is actually Weber per meter meter square. This will get cancelled out. This will be Weber per ampere meter. You can also write something like that. Okay. Hopefully everything is clear with this concept. The value I have also written down the value. Mu naught basically stands for permeability of free space. Permeability of free space or vacuum, right? So we have completed Biot-Savart's law. That's all what Biot-Savart's law stands for. We have already explained the cross product rule, the direction, dB, everything is cleared. Now we are going to talk about the application of Biot-Savart's law. Okay? Acha, by the way, if someone tells you to find out the direction of magnetic field, direction of magnetic field can be found out for two things. One is for a straight current carrying conductor. If you have got a straight current carrying conductor, align the thumb in the direction of current. Align the thumb in the direction of current. So the curled fingers will give you the direction of magnetic field. Right? So that means over here magnetic field is going to be cross, over here magnetic field is going to be dot. And you're going to draw magnetic field line something like this. That is concentric loops which are going something like this. Alright, and if you have got a wire which is actually circular, right? So we are going to talk about both of the things. We are going to talk about a straight current carrying conductor and we are going to talk about a circular wire. So if you have got a circular wire, your curled fingers will be in the direction of current. Will be in the direction of current and thumb will point in the direction of magnetic field. So this means that if thumb is pointing something like this, so let's suppose current is in this one is going to be anti-clockwise, thumb is pointing upwards, so magnetic field lines must complete a loop. The magnetic field lines are closed continuous loops. You might have heard this in grade 10. So these magnetic field lines are going to be something like this. Is it all good? Hopefully with direction of magnetic field everything's clear, and I want you to be really quick on these things, okay? Because when you are going to solve some problems now, we don't want here you have a slightest of doubt in finding out the direction of the magnetic field. So we need both the things. We need to find out the magnitude, that will be found out by Biot-Savart's law, formula, scalar form, and we can also find out the direction using Biot-Savart's law, cross product, and using this right hand thumb rule. Hopefully everything is clear. Now let's move on. So now we are going to talk about, let's say, we'll discuss the magnetic field due to a straight current carrying conductor. We have got a straight wire. I'll just write it in short. We have got just a straight wire. Alright. Although see, the derivation is not important. For you, you can simply learn the formula. But if you want to have a better understanding of things, you can actually see how these derivations works, right? Let's suppose we have got a current carrying wire, and right now we are not commenting on whether this wire is going to be infinite, semi-infinite. We'll just take a random wire, and let's suppose we want to find out the direction, we want to find out the magnitude of magnetic field at this point, because we already know what direction is going to be. Direction of magnetic field at this point is going to be just cross, right? At this point it's going to be cross, at this point it's going to be dot. So now what we can actually do is, again we'll say that here, let's suppose we have got a current element at this point. At this point we have got a current element, and it is actually at a distance of y from here. At a distance of y from here. So if this is y, my dear dosto, the length of this thing is going to be dy, right? And the angle which this dy element, by the way, what is this dy element I am talking about? Here this dy element is nothing but current element, okay? So this angle is angle made by the current element is and this position vector is let's suppose it is theta. This is r. And this is a point x, let's suppose. Alright, hopefully everything is clear. So if I want to find out the magnetic field due to this dy at this point, I'll say that your magnetic field is going to be dB, right? And that dB will be written as, if you'll all see that dB will be written as mu naught upon 4 pi I dy sin theta divided by, dosto, if I'm going to talk about the magnitude of this thing, the magnitude of this thing is going to be, this was by the way ideal sin theta upon r square, right? So this magnitude is going to be nothing but x square plus y square. That's it. It was root, the magnitude was root. We used to square it down, so this is going to look something like this. Hopefully everything is clear till this point. Acha, tell me one more thing. If I'll say what this angle is going to be, so you can say, sir, this angle is going to be just phi. This angle is going to be just phi. Also we can write one thing. There's going to be a slight manipulation over here. Also we can rewrite that tan phi can be written as perpendicular, that is y upon x, or y can be actually written as x into tan phi, right? So if I'm going to differentiate it with respect to theta, it will become x into sec square phi into d phi. Please see, this is the point where you can actually leave this derivation. They will not ask derivation in NEET exam, but if you'll solve these derivations, you will get to know why we actually try to differentiate a certain thing. The reason was that, see, we are trying to integrate y over here, and the thing that is changing is actually theta. So I cannot proceed like this. So I'll have to either change y into theta or theta into y. So I have done it, right? So instead of dy, dosto, instead of dy, I can actually write mu naught upon 4 pi I sine theta times, instead of dy, I am going to write x sec square phi times d phi, right? Acha, by the way, if you will closely see, if you will closely observe one thing, I can also write sine theta as sine 90 minus phi, which will be written as cos phi, isn't it? You tell me, isn't it, right? So can't I write this cos sine theta as cos phi? Yes sir, of course you can write it down, divided by, if you will again see over here, I'll take out x square common. So if I'll take out x square common, I'll be left with 1 plus y upon x is again tan phi, so this will be tan square phi. Now see, I can understand if someone of you is saying, sir, this is getting really complex. Now I can understand, I am with you. But please, I mean, you're not going to get any derivation at first. You'll always feel, sir, why are we doing it? Why are we doing that? So step by step, every time you go step by step, first of all, everyone should understand how we have written the Biot-Savart's law. Now I have explained here why are we doing something like that. Why are we doing something like that? Because we want our formula to actually be in a specific way, right? So again, 1 plus tan square phi, by the way, this 1 upon what I can say is, this 1 upon tan square phi will be nothing but sec square phi. Is it clear? Hopefully this is all clear. So this will become mu naught upon 4 pi I, one of the x can be cancelled out, I upon x. See, this is again, if I am going to give you from the very starting, we know that, yeah, that sine square phi plus cos square phi is 1. So if I'll divide everything with cos square, I'll get tan square phi plus 1 is equals to sec square phi. So can't I write, instead of tan square phi plus 1 equals to sec square phi, right? So I'll write it down over here. So this means that this whole thing will be cancelled out with this sec square phi, and I'll be left with cos phi into d phi, and this is going to be your dB. And if, let's suppose, I want to find out the net magnetic field, if I want to know what is the net magnetic field in this case, so I'll just do one thing, I'll just integrate it, and let's suppose I want to integrate it from theta 1 to theta 2. Now what are these theta 1 and theta 2, sir? We surely will have some limits over here, na? So let's suppose this limit is theta 1, this limit is theta 1, and let's say this limit is theta 2, this limit is theta 2, this thing is theta 2. So I'll integrate it from, so according to this, I'll integrate it from theta 2 to theta 1, right? Although let's do one thing, usually we see something like this is theta 1 and this is theta 2. So I'll write it something like that, theta 1 and this is theta 2. So I'll integrate it from sine theta 1 to sine theta 2, and just because I also want you to know that, sir, this is going to be minus sine theta 1. Why, sir? Why is that? Because here, please understand, whenever you are going to talk about direction, this is 0 degree line, है ना? Now if you are saying, sir, this is theta 2, I must say, na yaar, theta 2 can be, let's suppose this is 30 degree. So a 30 degree same angle will be on the upside also. So how would I know that I have to go 30 degree downwards? With using an angle, using a sine. So this will actually become mu naught I upon 4 pi x, and integration of cos is actually sine. So this will become sine theta 1 plus sine theta 2. Chalo, now please hear me out carefully. This means that, sir, what you are trying to say is, you could have just said that magnetic field due to a straight current carrying conductor is nothing but mu naught I upon 4 pi x. By the way, x is going to be the distance at which we are finding out, and this x is at a perpendicular bisector. Okay, this is at the perpendicular bisector, and this is going to be sine theta 1 plus sine theta 2. So this is something which you should remember. Fine, if you are having a little bit of tiny problems with the derivations, you are not a big fan of derivations, fine. We can live we can live with that. If you are having lots of trouble in derivations, fine. I'm not going to say that NEET is impossible for you. I'll suggest that if you want to have those marks, like for example, if you want to top the paper of NEET, if you are aiming for AIIMS Delhi, you should not be afraid of these things. I always tell my NEET students here, you are studying far more difficult things than these things. Okay? It might look frightening to you, but it is not. I mean, you are way what I can say above all of these things. Okay? So this is going to be mu naught I upon 4 pi x. You might also write it as d. I should have taken the variable d because generally in every book they use d or r, but okay, it is x. Fine. Now we are going to talk about something that some cases which are the special cases. So special cases are, for example, case 1. Case 1 is for an infinite wire. So please understand, if you have got an infinite wire, which would be something like this, that means both the ends of this infinite, both the ends of this wire are going to tend to infinity. Let's say plus infinity and minus infinity. And if you are going to ask me, sir, what angle are we going to get from here? Now this is very easy. These angles are going to be just 90 degrees. So theta 1 and theta 2 are going to be nothing but 90 degrees. Why is that? Think about it. If you will ask me, sir, let's suppose at a particular point the angle is theta 1. And now I am increasing the length. So I would say, okay, so now if you have increased the length, now angle will also increase. So if you are saying, sir, length is actually infinity, so I'll mark something like this. So I'll have angle as 90 degree, na? And similarly on the downside also. Clear? So if this is the case, magnetic field will be, and now I'm using this thing as D, so please don't mind. Magnetic field will be mu naught I upon 2 pi d, a very important relation which needs to be on your fingertips forever, like at least till NEET exam. Okay? At least till NEET exam. You'll say, sir, don't get senti, we'll never remember physics formulas for life. But okay, till NEET you must remember that magnetic field due to an infinite wire, and wherever they'll talk about, I've got a long infinite wires. Okay, so these are just the code names for these things. This thing can be also called as long infinite, sorry, just long current carrying wire. Long current carrying wires. It can be also called as something like this, or you can also rewrite this thing as mu naught upon 4 pi, so that you can use that this thing times 2I divided by d, right? So this is another type of, so please remember it. Now the next thing is case 2, when you have got semi-infinite wire. Do I need to draw the diagram for this also? Semi-infinite wire would look something like this, isn't it? So that means at one end it is going, it is moving towards infinity, and we want to find out the magnetic field at point P, and it is at there is a close end over here, right? So that means if I am going to talk about point P, if I am going to draw the angles, one of the angle is going to be 90 degree, sure, and theta 2 is going to be just 0 degree. So basically this magnetic field will be for a semi-infinite wire would be just the half of the previous one. So mu naught I upon, let's suppose this distance is also d, mu naught I upon 4 pi d. Just the half of the infinite wire, complete infinite wire. Hopefully this makes sense, right? Now let's talk about some of the numericals. है ना. Let's talk about some of the numericals from this topic, and these numericals are going to be sufficient for your NEET exams. What I mean to say is obviously practice some more, but this level is going to be sufficient enough. The question is saying calculate the magnetic field induction. Now please see here, sometimes students actually they feel the trouble with the terms. Sir, we used to call it as magnetic field intensity, now they are calling it as magnetic field induction, same thing. At a point distance a root 3 by 2, so that means you have got a wire, you have got a current carrying wire of length a, so you have got the length a, you know what the length is, and it is at a distance of, it is at a distance of a root 3 by 2. So the point is on the perpendicular bisector, that means this is a, this is a, right? So if this is the case, my dear doston, can't you find out this angle? Can't you find out this angle? Whatever this angle is going to be, we are going to have the same angle over here as well, because it is at the perpendicular bisector, right? By the way, initially I also said once time that it is at perpendicular bisector. It is perpendicular, it could not bisect it, right? Theta 1 and theta could be different, but in this one it is, these are same. So if I want to know, I'll simply write that tan theta is equals to perpendicular upon base. Hopefully everything is clear till this point. Perpendicular at a distance of a root 3 by 2. So perpendicular is a, and so this is going to be a by 2, my dear dost, hai na? This is not 2a, so this is going to be a by 2. What is going to be a by 2? The length from here till here, it is going to be a by 2. So this is going to be 2 over here as well, of course. So this is going to be 1 by root 3. So that means theta is going to be tan inverse 1 by root 3, which is actually nothing but 30 degree. So 30 degrees. So basically magnetic field comes out to be mu naught I upon 4 pi d. Instead of d, I am going to write something as a root 3 into 2 into sine 30 plus sine 30. So it is going to be 2 times of sine 30, that is 2 times of 1 by 2. This cancels out this cancels out this. Finally, the magnetic field comes out to be mu naught I upon 2 root 3 pi a. Take a look. Mu naught I upon 2 root 3 pi a. Alright, and the direction is going to be, of course, into the plane, right? Now let's move on to the next question. Figure shows a square loop made up of uniform wire. Find the magnetic field at the center of the square if a battery is connected between point A and C. So we have got a square, and see, if you can please see, we have got two types of wires over here. Magnetic field is going to be, if I am going to talk about this wire, magnetic field is going to be cross, magnetic field is going to be cross. For this one, magnetic field is going to be dot, magnetic field is going to be dot. Please understand two things, right? So because of wire AD, magnetic field is actually cross, and because of wire DC, magnetic field is cross as well. You can again do it. Thumb in this direction, open finger towards this, fairer end of your hand is coming into the plane, cross, cross. For this one, thumb in this direction, open your fingers like this, dot, dot. So these are going to add up, and magnetic field due to AB, this will be dot, and magnetic field due to BC, this will be dot. So these are going to add up, right? Hopefully everything is clear till this point. Now please try to understand that if you have got a square loop, can we also draw the angles? Like for example, if I will only use this diagram, let's talk about these two angles. This is going to be A by 2. This is going to be A by 2. So this angle is going to be 45 degree. Hopefully everything is clear till this point. So both of these will have same magnitude as B. Both of these will have same magnitude as B. This will be in cross. This will be in dot. So the net magnetic induction is going to be 0. Very easy thing. Hopefully no doubts. Let's move on. Acha, let's talk about this question. And now what I want is pause the video and do it by yourself. And then unpause it and check. We want to find out the magnetic fields at point A, C and D. So you have got 3 questions. I'll solve 2 for you and I'll expect you to solve at least 1 and write down the answer in the chat, in the comment section. Let's first find out the magnetic field at point A. So the net magnetic field at point A will be because of the vector sum of magnetic field due to wire 1 plus magnetic field due to wire 2. Now, obviously, we are going to talk about vector sum because magnetic field is a vector quantity. So, let's first find out the direction. Please see here, thumb in the direction of current, open the fingers like this. That means for 1, magnetic field is actually dot. For 2, current is going downwards. I'll open my fingers in this direction. Magnetic field is coming cross. So, that means there will be a negative sign. When I'm going to talk about the magnitude of BA, I'll write something as mu naught times 2I upon 2 pi into D. D is actually A minus mu naught. These are infinite wires. So I'm just using the formula of mu naught upon 2 pi D. Mu naught I upon 2 pi into 2A. Is that clear? So we have got 2 pi A, we have got 2 pi 2A. So I'll multiply 2 over here. So finally we'll get, this will be 4. So this will become 3 mu naught I upon 4 pi A. And what is going to be the net direction? This magnetic field is of course greater. So the net direction is going to be dot. Hopefully everything is clear, right? So this was the first magnetic field at point A. Now let's talk about magnetic field at point C. So magnetic field at point C, again it will be because of the vector sum of magnetic field at point 1, magnetic field due to wire 1 and magnetic field due to wire 2. So because of wire 1 it will be cross. Because of wire 2 दोस्तों it will be also cross. See both for 1 it is cross and for C also, for 2 also it is cross. So you are going to simply add them. So simply add them now. This will become mu naught 2I divided by 2 pi into D. So D is actually A by 2 plus mu naught I upon 2 pi. This is also going to be A by 2, right? So this will become actually 5 mu naught I upon 2 pi A. Now for magnetic field at point D, find out the answer, write down in the comment section, right? Quick. Now let's move on. To the next part. Next part is for circular loop, right? So if you are going to talk about circular loop, again you can actually derive it. First of all, I'll try to draw the diagram for you. The circular loop actually looks something like this. And this is the axis of the circular loop. and the current is flowing something like this. This is the center. So this is the axis of the loop. Please understand how this loop is. This is the axis of the loop. The loop is something like this. So this is a YZ plane. I call this as a YZ plane. So axis of the loop is on the X axis and the loop is itself on the YZ plane. Okay? So now let's suppose I want to find it out. Acha, by the way, we'll figure it out. We want to find out the magnetic field at certain point P. At this point, radius of the loop is actually capital R, and this distance is actually, let's say this distance is X. So if this distance is X, I'll take an element over here. I should mark an element first over here. I'll take an current element over here, which will be IDL, and now you tell me what is going to be the direction of IDL. So if this was the loop, IDL is going to have the direction towards you, towards the camera, right? Towards something like this, and the angle which this IDL makes with this position vector, by the way, this will have magnitude as R square plus X square and root of it. Do you remember that that Biot-Savart's law? Na? If I'm going to talk about the magnetic field due to it IDL at this point, I'll write something like dB equals to mu naught upon 4 pi I dl sine theta. This is going to be sine 90. Everywhere this angle is going to be sine 90 and divided by the square of the distance. So this will be something like this. This is going to be dB. But what is going to be the direction of dB? Can we use right hand palm rule over here as well? Now you will have to actually do it by yourself. So as I am doing it in front of you, please you also try to do it. This is the axis. This is the loop. At this point, direction of IDL is towards this. So I'll point my finger towards IDL. I'll open the finger towards the point I have to find out the direction of magnetic field. And if you can see, I have got a slanted palm, something like this. So at this point, magnetic field will be something like this. So this is going to be dB. And let's suppose this angle is D, this angle is phi. So this angle is going to be, I'll mark everything for you. This angle is going to be 90 minus phi. This angle is phi. So this angle is going to be 90 minus phi. So this is going to be dB sine phi. And this is going to be dB cos phi. Right? Acha, whenever we talk about something that is called as a loop, loop is a symmetrical object. So I'll have a same current element over here. I'll have same DL over here. So I'll have same dB over here as well. And these are just two. I've got infinite number of current element, right? So this is going to be dB. But the fact is that this will also be dB cos phi. So these are going to cancel out because of symmetry. And all the dB sine phi's are going to add up. So I'm going to write something like, if I want to know the net magnetic field at an axial point, I'll just write the integration of all the magnetic fields along x-axis. Or what I'll do is I'll write down something like this, mu naught upon 4 pi I dl. This is sine 90. I don't have to do this. See, the sine 90 and phi are two different things. That's why I have used different variables. So I'll write mu naught I dl sine phi upon r square plus x square. That's it. And if you'll closely see over here, I can write sine phi as perpendicular r upon hypotenuse, that is r square plus x square and root of it. Hopefully everything's clear, right? Tell me if you have any doubt. So now we'll be left with, I can take out this mu naught I. Instead of sine phi, I can actually write r. I can write r upon 4 pi. And I already have got r square plus x square. And then I have got also 1 by 2 over there. So this will become 3 by 2 multiplied by integration of dl, and if you'll integrate all the dl's, you are going to get something like mu naught upon 4 pi. I'll have over here as, this is going to be 2 pi r, so I'll have over here as 2 I, well I'll write something like mu naught I pi r square multiplied by 2, wherever you want to write it down, 2 divided by r square plus x square whole raised to the power 3 by 2. Now we can rearrange it. Okay, we can rearrange it. This is one of the way, mu naught I into 2 pi r square upon 4 pi. So the net magnetic field will actually, if you want to cancel these things down, the net magnetic field will be, first of all, it will be along x axis. This will be mu naught I, and this will become, pi can get cancelled out, r square upon 2 r square plus x square whole raised to the power 3 by 2. And if you've got n number of turns, then let's just write n over here as well. Acha, sometimes you can also write this pi r square as area of the loop. So sometimes we can also rewrite this thing as, one of the formula can also be made as B net mu naught upon 4 pi 2I A, so 2I into A divided by r square plus x square whole raised to the power 3 by 2. Alright, and n is the total number of turns. Now let's suppose one of the special case over here, if let's say x is far more greater than r. So if x is far more greater than r, so what we can do now is, we can neglect this r square, we can neglect that, hopefully everything is clear till this point. Yeah, I think we'll use another thing. We'll use, if first I'll write at center. Let's not use that case. First let's write at center. So at center basically means, that x will become 0, right? So if x will become 0, net magnetic field at center will be, please see, x will become 0, so this will become r cube, so this will be like mu naught I upon 2r. This is going to be your formula, mu naught I upon 2r. Have a look, direction, everything is clear. This is the thing which you need, which you will use the most, right? So when we talked about the direction of the magnetic field at the center, if you remember over here, right, we talked about something like this. So if someone will ask that, yeah, what is the magnetic field at this particular point? So you are going to say that at this particular point, magnetic field at the center is just mu naught I upon 2r. Now, till now we have learnt two formulas. Those two formulas are, one is this, which is very, very important, and sometimes students actually get confused in these two things. One is mu naught I upon 2 pi d. Another is mu naught I upon 2d or 2r. Two formulas mostly used, right? So please make a note of it. Magnetic field due to a, we have completed current carrying loop. Now the thing is, we'll also talk about a sector, and I'll explain it in a very easy way. Let's suppose for a loop at center, for a loop at center, magnetic field is actually mu naught I upon 2r, right? And this will, let's suppose the direction of the current is actually something like this. So magnetic field will be dot, right? Now let's suppose someone is asking about a particular sector. let's say they are saying that what about we have got something like this. And current I is flowing and this angle is actually theta in radians, and we want to find out the magnetic field at center O. So we'll have to write down a formula. Na? So I'll give you, without deriving it, I'll just use unitary method. Very easy peasy kind of a thing. We'll say for 2 pi radians, the magnetic field that we are getting is mu naught I upon 2r. So for 1 radian, we'll have mu naught I upon divided by 2 pi. So for theta radians, we'll simply have mu naught I upon 4 pi r multiplied by theta radians. So this is going to be the formula. The magnetic field at center due to this sector will be mu naught I upon 4 pi r multiplied by theta, and this should be in radians. That's it. So if you have got something like a quarter circle, just multiply pi by 4 over here. If you have got a semicircle, so let's suppose we are talking about a semicircular loop. A semicircular loop. So for a semicircular loop, theta will be actually pi. So if theta is going to be pi, you will simply have magnetic field at center would be simply mu naught I upon 4r. That's it. Because you will write it over as pi will get cancelled, and this is going to be half of the magnetic field due to a complete loop. If you have got a quarter circle, write pi by 4. If you have got anything other than that, write that angle. That's it. Direction will be found out by simply over here also direction of magnetic field will be dot. Acha, what about these things, sir? Will these wires will also have some will constitute some magnetic field? No. Why? Because let's suppose if you have got a wire, something like this, and you want to find out the magnetic field due to this wire at this point, which happens to be on the line. So magnetic field at point P will be 0 because this point lies on the wire. So sine both of the theta 1 and theta 2 are going to be 0. Hopefully everything is clear till this point. Moving on to the next one. So now let's suppose I'm giving you one example which, see, in CBSE board exam they have just now asked it. They can also ask the similar question in NEET also. What type of question is this? Generally what they do is they tell you that let's suppose we have got a wire, a semicircular wire like this, and we have got, this is a loop and we have got 2 wires, something like this, and these are meeting up at centers. These are meeting up at centers, something like this, and let's suppose you have got current I flowing from here and current I will go back over here. Now what will happen at this point, dosto? At this point, let's suppose this angle is alpha 1 and let's suppose this angle is alpha 2. So current will get redistributed. Some current will flow through I2, some current will flow through I1. Sorry, some of the current will flow through the lower part, some of the current will flow from the upper part. You know that, sir, current will flow more from that region where resistance is less, and where resistance is more, current will flow less. And if wires are uniform, we'll surely know, sir, this path will have larger resistance, this path will have lesser resistance. We know these things. Acha, if you are going to talk about magnetic field, net magnetic field at center, that's what we want to know. Net magnetic field at center will be magnetic field due to wire 1 plus magnetic field due to wire 2. Acha, magnetic field due to wire 1 is going to be dot. Magnetic field due to wire 2 will be cross. So let's find it out each one by one. Also let's find it out their ratios. If we'll talk about magnetic field due to wire 1, we'll simply write mu naught I1 divided by 4 pi into this is going to be the radius. So radius is same in both of them, r multiplied by दोस्तों alpha 1, right? Because this was the that's what the unitary method we have seen over here, mu naught I upon 4 pi r times theta, mu naught I upon 4 pi r times theta. So theta is pi 1. Everything's clear? Hopefully everything is clear. Similarly, we are going to write something like B2 equals to mu naught I2 divided by 4 pi r times alpha 2. Everything is clear till this point? Fine. Acha, how, any one of you have any doubt in this formula that sir arc length can be actually written as theta into radius, right? So if I'm going to talk about, see, I've got two things over here. Please try to understand. Try to understand what are we talking about over here. What we are trying to say over here is current. Both of these points are at same potential. Both of these points are at same potential. That is, this wire and this wire are connected between same points A and B, right? So what we are going to say now is that sir VA is actually I1 times R1 is equals to I2 times R2. This R1 and R2 are the resistances, not the radius. These are the resistances, right? So I am going to say that sir I1 upon I2 will be actually equals to R2 upon R1. And sir, resistance, if you remember, resistance actually depends directly on length and inversely on area. But because the wires are uniform over here, area is also same. So basically, because area is same, I am going to simply say resistance directly depends upon the length. So if this directly depends on length, this will be written as L2, this will be written as L1, right? So now please understand, please see, I am going to write something like over here as mu naught instead of I1. Instead of I1, I am going to write and see what I will do. I will actually take a ratio of these two things. I will take a ratio of these two things. So if I will take a ratio of these two things, I will get B1 upon B2, mu naught upon 4 pi can be cancelled out. I will be left with I1 upon I2 multiplied by alpha 1 divided by alpha 2. So instead of I1, I will write it as L2. Instead of I2, I will write it as L1. I1 upon I2, I can write that thing. Acha, multiplied by arc length alpha 1, sorry, theta, this thing, this theta alpha 1 will be written as arc length. So I've assumed arc length to be L1 divided by R. Sorry, divided by radius. Please remember that R is radius. So instead of alpha 1, I'll write it as L1 divided by L2. So L2 and L2 cancelled, L1 and L1 cancelled. What are we seeing over here? We are saying that magnitude of B1 is actually equals to magnitude of B2. Please pause the video. Please rewind if you wish. I have explained each and everything. Capital R is radius. R1 and R2 are the resistances. Okay? What does this mean? This means that the net magnetic field will be 0 at the center. Also, what you are seeing, sir, you have not taken any particular angle over here. That means no matter what these angles are, if wires are uniform, net magnetic field will be 0 at center always, no matter how you connect it. Okay? No matter how you connect it, this is going to be always 0. This means that if you have got a wire something like this, all of these wires are uniform. You are going to say, sir, right now the angles are actually 180 degrees, 180. So obviously, sir, we know that in this one, it is quite logical, sir, that it will be 0. Because I by 2 current will flow from upward part, from the top part, I by 2 will flow from the downward part. Net magnetic field will be 0 at this point. But even if you have got something like this, and let's suppose this is, in some question this is given as 60 degree, and this thing is given as 300 degree. In this also, always net magnetic field at center will be 0, always, 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 no matter what these things are. Even this will be true for something like this. For this as well, net magnetic field at center will be 0 for square, everything. All right, so please remember, this will be true for any geometrically symmetric loops that magnetic field at their center will be 0. Given, having said that, wires must be uniform. If wires are not uniform, things are going to be a little different, right? For example, as if let's suppose you have got two wires of different resistances. Let's suppose one is gold, another is silver. Now we know resistance of silver is less than that of gold. So current through silver will be less. So magnetic field through silver will be less. Magnetic field constituting through silver wire will be more, because current will be more on silver wire, right? Gold will be less. So now let's have a look at one of the questions, something like this. Let's suppose a square loop, we have to find out the magnetic field at the vertex P. Okay, so this is something different. We don't have to find out magnetic field at center, it is at vertex P. So let me name it, let me name something like this is point A, B, C and P. So magnetic field due to wire AB, first of all magnetic field due to wire PC and magnetic field due to wire PA will be 0, because these points are lying on the wire, on the same wire. Hopefully this is clear to all of you, right? As far as another two different wires are concerned, what we are going to do is we are going to say, let's suppose we want to find out the magnetic field due to wire BC. Magnetic field due to wire BC. So that will be mu naught I upon the distance is of course A. So this will be 4 pi A sine 0 plus one of this side is going, one of the this one is going to be sine 0. If I'm going to talk about this angle, is that clear? If I'm going to talk about this angle, this is going to be 45 degree. So this will be 1 upon root 2. So this will become mu naught I upon 4 root 2 pi A, and the direction is going to be at point P, direction is going to be dot. Now let's do the same thing for magnetic field due to wire. This was for wire AB. Sorry, just a second. So the thing is, we always, this is absolutely correct. now we are going to talk about another angle. So this is going to be 45 degree as well, and this is also going to be dot. So wire AB will also be same as this, mu naught I upon 4 root 2 pi a, and this will be also dot, right? Because of this also it will be dot, because of this also it will be dot. So the net magnetic field will be 2 times of mu naught I upon 4 root 2 pi a. So that will be 2 mu naught I upon 2 root 2 and a dot. So option A is going to be absolutely correct. Option A. Fine, everything's clear. Quickly tell me in the chat box if everything's clear. I'll again explain how you are going to mark the angles. Let's suppose if this is the wire and someone says that we have to find out the angles. So if this is the point, from the point we mark the wires. So if this was the point, we mark the wire. So one of the point is going to be over here, another point is going to be over here. So this angle is again going to be 45 degree in the second case. For this wire, this one is going to be again 45 degree, this one is going to be 0 degree. Hopefully everything is clear. Moving on, my dear friends, you are going to see many problems something like this, right? And when you are going to see something like this, they are saying that find out the magnetic field at point O. So magnetic field at point O is due to how many elements? See, these two straight wires will constitute no magnetic field because that point O is on the line. Whereas the bigger loop will have a magnetic field of dot, and this one will also have a magnetic field of dot. Both will have a magnetic field of dot, so we'll simply add them. So we'll write mu naught times I upon 2r plus mu naught times I upon 2r. So I'll multiply 2 over here. So this will become 3 mu naught I upon 4r, and the magnetic field is going to be dot. That's it. Hopefully everything is clear. Acha, sorry, by the way, one mistake I've done it. I'll also have to multiply a 2 over here also. Why? Because this is a semicircular thing. So this will become 8. This is a semicircular loop. So this is mu naught I upon 4r is the formula. 4 times radius. Now let's talk about Ampere's circuital law. Ampere's circuital law is analogous to your Gauss law. Whatever you have learned in Gauss law, Ampere's loop will help you in a similar way. What does Ampere loop says? Ampere loop says, we'll learn about it, but right now let's see. Ampere loop say, let's suppose that we have got certain current carrying wires over here. Something like this. So let's draw a loop, something like this, right? I mean, if you want me to actually draw a perfect loop, you know what I'll do is, I'll actually something like this, right? And let's suppose these are wires which have current I1, I2, I3, I4 and I5. Now this law says, Ampere's law says, the line integral of B dot dl will be equals to mu naught times of enclosed current or net current through the loop, which in this case net current will be, so you just assume a particular direction. So I1 plus I3 minus I2 is going to be the net current. All right. And if you're going to draw another cross section diagram for this same loop, it would look something like this. This is the same diagram. So let's suppose I1 is going out. So I'll draw I1 something like this, I3 something like this, and I2 something like this. All right. Now again we can discuss the applications of Ampere's law. We can talk about a current carrying conductor. Is that clear? We can talk about an infinitely long wire. An infinitely long wire, something like this, and we have to draw an Ampere's loop over here. So an Ampere's loop will be simply drawn like this. Now you know how we are going to talk about loop. Acha, one thing, when you are going to talk about the line integral of B dot dl, so this is going to be B dot cos theta equals to mu naught times of I enclosed. In this case, this is going to be just I. Let's suppose current I is flowing through this wire. What is this B dot dl, right? Everyone knows what is going to be the direction of magnetic field. Direction of magnetic field at this point is going to be cross. And what is going to be the direction of dl? So direction of dl is actually tangential to the loop. So this is tangential to the loop. So angle between magnetic field and dl is actually 0 degree everywhere. Please understand, this is how you are going to take particular loops over here, right? So this will be always 0 degree. This will be cos 0 everywhere on the loop. So we'll have something like B dot integration of dl, which will be 2 pi into d. Let's suppose we want to find out the magnetic field at d distance. So we have made a loop of d radius equals to mu naught I. So same formula you are going to get from here as well. Mu naught I upon 2 pi d. Right? See, good questions are going to come from this particular thing for a solid cylindrical wire. If you have got a solid cylindrical wire, then things becomes a little different. You have got two types of wire. We can also talk about an hollow cylindrical wire, right? Let's first discuss a hollow cylindrical wire. So if you are going to talk about a hollow cylindrical wire, it basically means, we have already commented on the shape of the wire. It is a cylinder. The thing is that it has got nothing inside. I mean, there is no material, so there will be no current inside the solenoid. So that means current only flows through the boundary. So now if you are going to talk about magnetic field at 3 points, let's suppose magnetic field inside, magnetic field on the surface, and magnetic field outside. So you are going to use Ampere's loop 3 times. So if you are going to draw magnetic field at inside point, let's quickly draw it. Let's suppose we are drawing an Ampere loop something like this at some distance. But the thing is, there is no enclosed current. So this is going to be 0. As there is no net current is 0. If you are going to talk about at the surface, it will again come out as mu naught I upon 2 pi r. If you are going to talk about at any point other than this, it will become as mu naught I upon 2 pi small r. That's it, dosto. What else is remaining, right? So if someone is going to talk about the graph of these things, please don't get afraid with graphs now. Everything is similar to what you have done in electrostatics. So let's suppose we are talking about so this is R equals to capital R, and this is magnetic field mu naught I upon 2 pi capital R, and after this point magnetic field will be something like this. magnetic field will be inversely proportional to R. But what will happen if we have got a cylindrical wire? If we have got a cylindrical wire, something like this, now the current is flowing all over the body. That means that inside also we have got current, and the total current is actually I. That's what we know. Okay, radius is R, total current is actually I. Now if someone says that we have to find out the magnetic field at an inside point, so we will say that first of all, if we want to find out the magnetic field at an inside point, we'll simply say that magnetic field dot 2 pi into small r equals to mu naught times of I net. Now in this case, this will become B into 2 pi r equals to mu naught. Now this is where we will use a concept of current density. That total current is I, total area is pi r square, and we want to find out the current through pi into small r square. So this get cancelled out, one of the r will get cancelled out, and magnetic field at any inside point will come out as mu naught I upon 2 pi r square. Now what we can see over here is that magnetic field is actually directly proportional to small r. Of course, still it reaches the point of at surface. So at surface it will become maximum. This will be again mu naught I, mu naught I upon 2 pi into r. It will again become something like this, right? Hopefully everything is clear. And after this, it will again be at an outside point, it will be just mu naught I upon 2 pi into small r. So if you are going to talk about the graph for a solid one, the graph would look something like this. We have got small r over here, we have got magnetic field at this point. So from origin to this point, magnetic field will actually increase. And at small r equals to capital R, magnetic field will be maximum, and at this point this will now decrease. So this is 1 upon r, and this is directly proportional to r, right? So please remember all the graphs as well, and you don't have to remember it if you will understand these things. Acha, for solenoid, why solenoid is important for us? Just because we are going to use solenoid from here till we'll talk about like electromagnetic induction. So this is actually important for us. Although now this derivation is very simple, so I'll try to skip this derivation. I'll hope you'll not complain, because this is one of the most easiest derivation. I am supposing that you will get it, but still this is important for us. Let's suppose that we have got a current carrying solenoid. Now what are the different terms that we must remember in a current carrying solenoid? First of all, let's suppose that a current is being thrown into this solenoid, something like this and something like this, right? We must have a battery or a current source. I'm not drawing that. So the current is something like this. So two or three things. First is the direction of magnetic field. The direction of magnetic field in a solenoid is in the center is actually is uniform. That's what the correct word is going to be. It is uniform. That means magnitude is same all over the places and direction is also same. And after this, it will like any other magnetic field, it will try to form a closed loop. Right. So at the center, magnetic field is uniform inside, and the value of this magnetic field comes out to be mu naught Ni, where N is the total number of turns, divided by total length. Total number of turns divided by total length, right? And why only direction of magnetic field is something like this? That is actually something important, something which is important. So direction of magnetic field is found out by something that is known as clock face rule. So you try to hold this solenoid with your right hand such that fingers are in the direction of current. So thumb is going to tell you the direction of north pole. So this is going to be the direction of north pole. This is going to be the direction of south pole. All right. So if you want to write it down in the terms of capital N, so this will be actually small n will be actually equals to capital N divided by L. So magnetic field can be also written as mu naught N into I divided by length. Hopefully everything is clear till this point as well. Now we can actually look at one of the question. Question says, in a coaxial straight cable, the central conductor and the outer conductor carry equal currents in opposite direction. The magnetic field is 0. Please you do it by yourself. I'll do it. I'm not saying I'm not doing it, but pause the video and try to solve it. By the time I'll draw the diagram, they are saying something like this. Let's suppose you have got something like this, and now they are saying that we have got central conductor and the outer conductor carry equal and opposite. So central conductor, that means we have got current over here. This is the outer one, and we have got also in current in the inner conductor, and both has same current I, right? So they are saying that where the net magnetic field is going to be 0. That's what they are saying. So bhai, if you are going to draw an Ampere loop over here, and an Ampere loop something like this, if you draw only an Ampere, if you will draw an Ampere loop something like this, this will have net current as 0. This will have net current as 0, right? So outside the cable is going to be the answer. Please check. Please check. So let's move on to the next part now. Friends, now let's talk about the second half of this chapter, that is moving charges in a magnetic force on a moving charges, or when a moving charge is moving in a magnetic force in a region of magnetic field, it experiences a force. We have started our class with this thing. Okay? Now that force, that magnetic force will be written something like, now this is where you don't have to worry about derivation and all, right? Wherever there is derivation, I always perform that derivation. So magnetic force will be written as Q times V cross B. This is going to be the value of magnetic force. Now what we can see from this force? This force basically says that magnetic force is perpendicular to the plane of V and B. This is the first thing. All right. So magnetic force is also perpendicular to velocity, right? This basically means that magnetic force is also perpendicular to velocity and magnetic field also. So this would imply that this force will only change the direction. This force will only change the direction and after this we are going to say, we are going to let's suppose we are assuming an example over here. This thing can be also written in scalar form as QVB sine theta, where theta is the angle between V and B. So I'll draw the case 1 over here only. Case 1 is something like this. Let's suppose you have got magnetic field region and this is uniform magnetic field. So I'll also write this thing down. This magnetic field is perfectly uniform. And case 1 says that velocity is perpendicular to magnetic field. This means that a charged particle is being thrown something like this, and when charged particle will be thrown something like this, this is the direction of velocity, this is charged particle Q. Direction of force will be found out by V cross B. Again I will tell you to use V cross B before you use this gang sign. Is that clear? Right? So V cross B means velocity cross B. So thumb will tell you the direction of force. That means on this particular charge force will act in upward direction. So this is going to be magnitude of direction of magnetic force. Now instead of going in a straight line, this will start to move, and also as it will start to move, direction of magnetic force will also start to change, but it will always act perpendicular to the velocity. That means it will always act towards a center, and this particle will start to move in a circular path. Something like this. Right? So if you want to know the radius of this circular path, what we are going to do now is we are going to simply say that this magnetic force, which is QVB sine 90, will basically provide the necessary centripetal force, that is mv square by r. One of the v can be cancelled out, and the formula of radius can be written as mv divided by qb, or under root of 2m kinetic energy divided by qb. So these are going to be the two formulas, right? Also this is now very important. Please remember these formula. Questions are usually asked from this particular thing. Now we can talk about all of the other things, like for example as time period. Time period will be 2 pi r by v. So 2 pi r means 2 pi m divided by qb. Velocity is cancelled. What you need to remember in this particular point is that time period is independent of speed. Alright, time period is independent of speed. So, well, also some few more important things from this particular concept. If this is the case, this would basically means that the work done by this magnetic force will be 0, and so will change in kinetic energy. That means there will be no change in kinetic energy. When this particle will reach to any point, if you want to find out the speed of this charged particle, it will remain v. Velocity will change, right? Velocity will change. That's why we are saying that there is an acceleration, there is a force acting on it. But that force is only changing the velocity, not the kinetic energy. Now after this, you can also talk about case 2. Case 2 basically we mean to say that now the charged particle is not thrown in a transverse nature. Now let's suppose we have got magnetic field something like this. we have got magnetic field something like this. And now the charged particle is thrown at certain angle. This is the velocity and the angle is actually theta. So if angle is theta, we can do two things. One is going to be V sine theta. This one is going to be V cos theta. This will be Vx. This will be V sine theta. That is Vy. Out of these two components, please understand that this is parallel to magnetic field. So it will suffer no change. This velocity, the direction of this component, because of this component, the particle will start to move in circles, right? So magnetic field is like this. If there was only this velocity, the particle would have gone something like this in a circular path. But it has got also velocity in this direction, so it will move something like this. This is called as helical path. So it will start to move in helical path, right? And this distance between two complete revolution is known as pitch. Not delta x, just x. This is something that is known as pitch. Now if you want to write down all the other formulas over here, you can write it down. Now this is again very easy. See, similarly, radius of curvature is going to be just m v perpendicular divided by qb. So this is going to be m v sine theta divided by qb. Or time period is independent of speed, so it will remain 2 pi m divided by qb. If you are going to talk about pitch will be the velocity which is responsible for taking this particle in this direction is v cos theta. So v cos theta times time period 2 pi m divided by qb, because in one time period it will reach from here till here. So the distance between this is going to be the speed in this direction multiplied by time. So these are the formulas that you can actually use while solving the questions. Alright, so hopefully this will also help you. Now we can also talk about something that is called as Lorentz force. So Lorentz force, we are going to talk about Lorentz force when there is a combination of electric field and magnetic field. So it's quite easy. So if you have got a charged particle moving in both electric field and magnetic field, you are going to write the net force as the vector sum of electric force, electrostatic force plus magnetic force. So this will be, net force will be QE plus QV cross B. Now you can have different cases over here. I am not going to explain all the different cases, that if a charged particle is at rest, if a charged particle is at rest, no magnetic force. Electrostatic force will still be applicable. If a charged particle is moving, let me write one or two cases. Let me write one or two cases for you so that you can have a good idea. Let's suppose in first case, we are saying that charged particle is moving, but charged particle is moving parallel to magnetic field. So if it is moving parallel to magnetic field, this would mean that magnetic force will be 0. So there will be only, the net force will be only equals to QE, and this will be in the direction of electric field. Right? V is parallel to B. Case 2 can be, I'll explain the case 2 as velocity selector. Let's suppose we have got a charged particle which is moving like this, and we want this charged particle to actually move undeviated. We want this charged particle to move undeviated. Acha, also we have said one thing, that let's suppose that magnetic field is something like this. So if magnetic field is something like this, by the way, this is a positive charge particle. If it is a negative charge particle, you also one more thing, I have not explained Fleming's left hand rule. You can also use Fleming's left hand rule for these cases. Magnetic field is like this. Middle finger stands for current. So in whichever direction the positive charge particle is, current is going to be in the same direction. So thumb will tell you the direction of force. So thumb will tell you the direction of force, so something like this. So this is going to be magnetic force. Now, if we want that the charged particle should move in a straight path, it means that the net force must be 0 on this charged particle. Then only we can say that the particle will not change its path, because then the acceleration will be 0. And if it is a positive charged particle, then we'll say then electric force should act something like this. So this should be the electric force. And for that, electric field should be in this direction. So now the thing is, we are going to simply say QVB should be actually equals to QE. Q can be cancelled out, and velocity should be E by B. So it's really not about if you apply the electric field and magnetic field, charged particles are going to move in a straight path. It is a very specific case. Let's suppose we have got many charged particles, right? And we want to find out a charged particles with a certain velocity. And that certain velocities can be found out using the ratio of E by B. So let's suppose if there are certain charged particles who have velocities greater than E by B, then what will happen is, if it is greater than E by B, then there will be more electric force on it. So those charged particles will move something like this. That means some of the charged particles which have more velocities, they will move actually, as you can see, those will move in this direction. Those have less velocities, those will move in this direction, and which have got exactly V equals to E by B, those will move undeviated. Alright, so this is for velocity selector, a case for Lorentz force. Now let's talk about some questions on this as well. An electron is projected with uniform velocity along the axis of a current carrying long solenoid. So current carrying long solenoid means that the magnetic field in that solenoid will be something like this, and it will be of mu naught Ni. I'm just writing the direction of it. Then they are saying then an electron is projected with uniform velocity along the axis. So electron is also projected along this axis only. So by if electron is projected with this axis, there will be no magnetic force. Right? So electron will be accelerated along the axis, electron will continue to move with uniform velocity along the axis. Option B is absolutely correct, because there will be no force, no acceleration, so it will not deviate. Hopefully everything is clear till this point. Let's move. Acha, now we have got something which is actually a very important thing, which is force on a current carrying conductor. I have got some more questions, don't worry, we'll solve some more questions, but let's also complete this particular topic. See, if I have got a current carrying conductor in a magnetic field, something like this. Let's suppose I've got magnetic field, and this magnetic field is, by the way, uniform. And let's suppose I've got a wire something like this from point A to point B. So there will be, if you have got force acting on a charged particle, on a moving charged particle. So current carrying conductor is also basically it is also moving charges. Now electrons are moving, are flowing, or we can also talk about flowing. So in that case, if you are going to talk about force actually acts on it, and the value of force is dF equals to I dl cross B. I dl cross B. Although we can actually derive this formula, but those derivation, personally I think that you can also learn this thing without derivation. If you want me to derive it, it's quite easy actually. We'll use nothing but magnetic force magnetic force on one electron will be E V cross B, right? Is that clear? And because we are talking about one electron, let's just talk about as dF, right? Now this V can be actually written as, dl by dt. Also for, let's assume it for, not for an electron but for a small charge, that is dq. So dq by dt can be written as I dl cross b, but still you are going to find some another derivations also. That's why I'm saying that we can get away with this formula, I dl cross b. The important thing to note over here is that this dl is actually this displacement vector between point A and B. This is what dl is, the shortest path, right? Because this holds quite importance. The reason is, let's suppose if you have got a closed loop, something like this. This is a magnetic field region and you have got a closed loop, a current carrying closed loop. So from this fact we are going to actually say that on a closed loop, net force will be 0. Net force will be 0 as dl is 0. This is something important. Torque may act on it, may or may not. Torque may or may not act on it, but net force will be 0 on a closed loop, right? So, and if you have got a straight current carrying conductor, let's suppose that if you have got a straight current carrying conductor kept in magnetic field, so magnetic force on this wire will be BIL. As we can see that current, the direction of current element, the angle between current element, now wherever you are going to write see IDL, that is current element, the direction, the angle between current element and magnetic field is 90 degree, else I would have written it as IDL sine theta. The magnitude is going to be IDLB sine theta. Here sine theta is sine 90, that is 1. So BIL. And what is going to be the direction of this force? Again, you can use left hand rule. Magnetic field, current, so force will act in this direction. And value is going to be BIL. Right? Using this concept, we are going to actually define some of the things like force between two parallel current carrying conductor, which is a very important topic for this chapter, right? Very important. And how we are going to define it? Let's suppose you have got two parallel current carrying wires. Let's say they are infinite. Okay, let's say they are infinite, and we have got, this is, let's suppose this is wire 1. It has got current I1. This is wire 2. It has got current I2. Wire 1, wire 2, and they are at a separation of D. And we want to find out force acting on one current carrying conductor because of another. Now hold on, let's go step by step. Till now we have studied, sir, there will be a magnetic force acting on a current carrying wire which is kept in external magnetic field. So let's first find out what force will act on wire 1 due to wire 2. So that's how we are going to name it. So this is nothing but this is force on wire 1 due to wire 2. So that means if I'm going to write it down, I'm going to write it down something like this. This is going to be B, magnetic field of which wire? If you will write magnetic field of that wire itself, magnetic field of the self wire will not apply any force. So this is going to be magnetic field of wire 2 times current I1 times current length of L1, and direction we can find it out. But first let's find out the direction of magnetic field. So let's say this is I2. So direction of magnetic field because of wire 2 on this side is going to be cross. So that's why I'm using yellow color. Yellow color will only tell me the direction of magnetic field due to wire 2. Right? Now magnetic field is somewhere over here. So forefinger outwards, current is moving upwards. So there will be a magnetic force on this wire in this direction. So this is force on wire 1 due to wire 2. And we are going to write something like, this will be written as B2 will be written as mu naught I2 upon 2 pi d into I1 times L1. This, what is this L1? This L1 is nothing but we are assuming some length on this wire. So instead of this, let's write, now let me break this question in two parts. If this wire is applying a force on this wire, then wire 1 will also apply a force on wire 2. Let's suppose that is F21, and because they are forming a pairs, they will also follow Newton's third law. That means force on 1 due to 2 will be negative times of force on 2 due to 1. That means their magnitude will be same. So let's call them as F. So this F upon L will be called as force per unit length. This F upon L will be called as force per unit length, that is small f, and this will come out to be mu naught upon 4 pi. I'm deliberately writing it as 4 pi times 21 I1 I2 upon d. So this is going to be something that is called as force per unit length. Acha, this will be same for the another wire as well. Acha, you can check also. Let's suppose that this is current I1. So because of this current, this wire, magnetic field at this point will be cross everywhere. So magnetic field is inside, current is this side, thumb is going to point in this side. So magnitude will be same, direction is opposite. So they are attracting. This means that this is a very special note. If current are in same direction, that means wires are going to attract. So this is something indifferent to what you have been learning so far. Generally we say that, sir, like charges repel, like poles repel. Here it is different. If current are moving in like direction, they are going to attract, right? And if in opposite, they are going to repel. And using this formula, you can actually define what 1 ampere is going to be. So 1 ampere is that current flowing in two parallel current carrying wires. Now hear me out carefully. 1 ampere is that current flowing in two parallel current carrying wires separated by 1 meter when they experience a force of 10 to the power 2 into 10 to the power minus 7 newtons. Think about it. I'll not repeat it. I think I've got it over here. 1 ampere. Think about it. All right. Now I think what we can do is we can solve some questions. For example, as do we have the ratio of magnetic field? This is in homework. Please solve it in homework. This is magnetic field question. I think you can do it. What about this one? A 2 ampere current carrying straight metal wire of resistance 1 ohm, resistivity 2 into 10 to the power minus 6 ohm meter, area of cross section, mass is given, is suspended horizontally in mid-air by applying uniform magnetic field B, then magnetic field B is going to be. See, when you are going to see these kinds of problem, now don't you worry. Let's suppose this is a current carrying wire. Okay, I have drawn it as a rod. This is a current carrying wire. One thing is for sure, mg will act downward. Whatever you say here, mg will act downward, है ना? Mg will act downward. So to balance this, if we want to balance this in mid-air, a magnetic force must act on it, and magnetic force means that it is going to be BIL. Is that clear? BIL. Because we know that they have also given us 2 ampere. So current is given to us. 2 ampere is given. Okay. Then everything else is given. G value is given. We want to find out the length. So for finding out the length, you know what I am going to do? I am going to use the value of resistance. Resistance is actually equals to rho L by A. Resistance is 1 ohm. So length will be actually 1 ohm multiplied by area. Area of cross section is 10 millimeter square. 1 millimeter is 10 to the power minus 3. So this will become 10 to the power minus 6 divided by area of cross section. Sorry dosto, area of cross section was this. Resistivity is given as 2 into 10 to the power minus 6. So this can be cancelled out. This will be 5. So this will be 5 meters. Please check my calculation. You have any doubt, write down in the chat box. And by the way, this mg will be 500 gram. That means 0.5 kg multiplied by, thankfully they have given us gs 10. So this will be 1 Newton. So we have found out what L is also going to be, right? So now let's just substitute the values. So BIL, so B basically means BIL will be equals to mg. Magnetic field is, that's what we need to know. Magnetic field will be mg, that is 1, divided by current, that is 2, multiplied by length, that is 5, right? So what I can now do is I can multiply 100 and I can also write down 10 to the power minus 2. So this will be 1 into 10 to the power minus 1 Tesla. Have a look at it. Let's check everything is clear or not. Acha, there is one correction. Na? This is not, sorry, you have been seeing this for quite a long. This was not, I assume it to be 2. This is going to be actually 5 Newton. So this is going to be 5 Newton, my dear dosto, right? This is going to be 5 Newton. So this is going to be 5. Good. Everything else is correct. Concept was absolutely correct. There was a slight error. Now let's move on. See, now we have got something which we are going to also use in our next chapter of magnetism and matter, which is called as magnetic moment. Magnetic moment is nothing, is not a very difficult thing. First of all, it is a vector quantity and direction is, the value is I cross A. So let's suppose you have got a current carrying conductor, something like this. If you have got a current carrying conductor, something like this. So magnetic moment will be in this direction using your normal right hand rule, right? It is a vector quantity. What else we can talk about it? We are going to use it in when we'll discuss about torque and another kinds of formula, right? So other than that, there is nothing really important. Unit is going to be ampere meter square. Remember, the SI unit is going to be ampere meter square. That's it, right? Nothing to worry about over here. Acha, now let's talk about torque on a current carrying loop. This is the one of the last topic of this chapter. Almost I have completed everything in this 2 hours. See, I don't want these one shots to be really long. I want that in 2 to 3 hours you can get almost everything from a particular chapter. Okay? So let's say dosto, we have got magnetic field over here, something like this. Magnetic field, something like this, and we have got a current carrying loop which looks like a rectangular loop. Okay, something like this dosto, and this is actually P, Q, R and S, and I'm going to talk about 2 things over here. So I'll make a copy of it also. Now please see. This is a current carrying loop. So that means it has got current I flowing something like this. If someone will ask you, can you tell me what is going to be the magnetic moment in this case? Yes, let's say the length of this PS is A. This is, let's say, this is, let's say, this is A, and this is, let's say, B. So area of this loop is A into B or AB. So magnetic moment will be I into AB, and the direction of magnetic moment is going to be something like this. Are you getting it? Into the board. So magnetic moment will be actually cross. Hopefully you are able to understand it, right? Now if I am going to say what is the force acting on QR, let's discuss what is the force acting on QR side, because it is a current carrying wire. It will be 0. Why? Because current and magnetic field are in same direction. So BIL sine theta, sine 0. Similarly, there will be no force on this PS also, right? Similarly, there will be no force on this PS also. But when we are going to talk about force on this PQ, magnetic force on this PQ, it will be BI into A, and the direction, doston, please do it with me. Magnetic field is in this direction, current is in this direction, so force is going to be, doston, force is going to be in this direction. So this is force on PQ. By the way, on RS, force will be outwards, so force will be on RS, something like this. So that means this is going to be cross, this is going to be RS, so this will be BIA, this will be dot, so they will create a moment, not a moment that you are thinking about. They will create a torque, all right? They will behave like they will create a torque, and this torque can be written as F into R perpendicular. So F is BIA and R perpendicular is going to be, doston, R perpendicular is going to be this. So that is B. So this is going to be BI into area. Deliberately I am writing it as area. Now I will write it as A, capital A. So this is going to be torque. And now let's suppose I can also write it as IA as M now. So this I can write it as MB. Or if there are n number of turns, I can write it as BINA. But we have got a little condition over here, a case over here. This is when the magnetic moment is perpendicular to what we can say to magnetic field, right? What will happen if it will make certain angle? That is the different case, right? So instead of drawing a loop like this, what we are going to do is we are going to draw a general case. Although first it is good to talk about a specific case. Acha, by the way, what is the direction of torque, sir? After having all of these things, also explain the direction of torque. Yeah, everyone knows it will move something like this. This is actually clockwise, and can we see it using M cross B? So M was like this, magnetic field like this, and then cross B. So aren't you getting it is clockwise, dosto? This was magnetic moment cross B. So this can be also written as M cross B, that we are going to talk about in the next part. So let's say we have got, now it has been rotated at a certain angle. So rotated at a certain angle basically means something like this. So dosto, can you please see that now the area vector is going to be something like this. The area vector will be perpendicular, and now the area vector, or the you can also say that, sir, this is what the magnetic moment you are talking about, same in the same direction I mean, and the magnetic field are making some angle that is theta. Are making some angle that is theta. Right? This is area vector. This is magnetic field. They are making some angle theta. So if they are making an angle theta, the distance between these two forces will become, this will not be now B, but this will be now B sine theta. Think about it. It's easy trigonometry, dosto. This will be B sine theta. This distance will become B sine theta. So now the torque will become BIA times small b sine theta, and if we are going to talk about n number of terms, it will be BIA n sine theta, or I into A can be written as M, so this will be acha, just a second. First of all, let's talk about these things. First, let me write sine theta. I'll talk about number of terms afterwards. So this will be actually MB sine theta, or simply M cross B. That's how you will find out the direction of torque. And now if there are n number of turns, just multiply Bina sine theta for n number of turns. Hopefully everything is clear, dosto. No more doubts. See, for all of those work done, all of those things I'm going to talk about in magnetism and matter, not here. That is part of dipole, magnetic dipole. We are not going to discuss that over here, right? We studied this torque on a current carrying loop because we are going to use the same thing in a moving coil galvanometer. First of all, a very easy question for you in homework. Acha, unstable equilibrium, not going to talk over here. Not going to discuss it over here because this is something which we are going to discuss in magnetism and matter. Acha, moving coil galvanometer, everything is covered. Conversion is already covered in current electricity. Please see why I covered that over there, because parallel and series was done over there, hai na? So I completed this particular part in that chapter. Acha, galvanometer is basically, it works on the principle of, if you are going to talk about in what principle does it works. So principle is basically that torque acts on a current carrying loop kept in magnetic field. Acha, now let's talk about something about its structure. Here we have got a very small hairpin. Here we have got a spring attached over here, and this is a cylinder, non-conducting cylinder, in which we have wounded wires through which the current is going to pass. And as we know that galvanometer is a highly sensitive device, is a very sensitive device, like you all are sensitive device, which measures current. Just joking, I am also sensitive. Which measures current, and this current is actually very small current, right? So how does it works? It works on the principle that, let's suppose that we have got something like an arrow attached to this cylinder. Now as the current is going to pass, we are going to say that, see, current carrying conductor is kept in magnetic field, and this magnetic field is radial, by the way, right? So this is going to move. So as it is going to move, there will be a torsional strain developed, which we are going to call as restoring torque. This is something that is called as restoring torque or torsional strain. Because of torsional strain, there is a restoring torque, and this will act in the opposite direction to the rotation, and at a certain point, this thing can be actually written as, the magnitude of this torque can be written as k theta, and at a certain point, this k theta will become equals to Bina, and over here sine 90 will be 1, the theta will be 90 degree, because we are using radial magnetic field, and theta upon I is actually known as current sensitivity. which is actually nothing but theta upon I will be BNA upon K, right, which is actually current deflection per unit current. So if you want to increase current sensitivity, you can increase it by increasing the number of turns, but by increasing the number of turns, resistance will also increase, right? And again we have got something that is known as voltage sensitivity. So voltage sensitivity is basically theta upon V or theta upon I into R. All right. So this thing again can be written as current sensitivity divided by R. All right. So with this dosto, now let's end today's class. Hopefully under 2 hours, this you have got to know a lot about this chapter. This was beneficial for you. See, I'm going to come up with another series also in which in those series will be specifically talk about only numericals, right? So this is a mix up of numericals and concepts. Now let me know what's your feedback on this, and if you have got any other demand, please communicate with me. I'm Subrat Sharma. I'll be teaching you physics in pure English. So if you have any more concerns, see, we have got NEET 2025. For that, let's now move every stone. Okay, let's not miss anything. Let's be really disciplined. Through this platform, we will be able to get a very good rank and a very good seat in top medical college. Okay, so with this positive note, I'll take your leave. Thank you so much. Bye bye.